Welcome all. Today I'll take questions on heat transfer. This is a question series for GATE 2023. So actually, some questions are very good questions. Some questions are simple. But why I have taken those simple questions is there is a reason. So sometimes the figure or the data may be confusing, but it is very simple. So I'll give one first question. Let's take a simple question, but some students may get confused. Straight away, let us get into the subject. Okay, chalo. First, we'll take this question. Very simple question. One second, please. 1 second, please. Where is that question? Where is that? Today I have taken some very good questions. Uh, yeah, just see this question. Just see this question. Now, in a double pipe heat exchanger of 10-meter length, focus on this length. Let me repeat. So this length, the length is 10 meter. A hot fluid flows in the annulus and a cold fluid flows in the inner pipe. The temperature profiles of hot and cold fluid are given along the length of the heat exchanger. This is the temperature variation of the hot fluid along the length of the heat exchanger or pipe, and this is the variation of temperature along the length for the cold fluid. And please note down that the variation of temperature with the length, X stands for length. So if this is our heat exchanger, this is your pipe and this is the annulus, and both fluids are flowing like this. Look at carefully. Now, at the inlet section, so just by looking at this question, you may get confused. So far, we have solved logarithmic mean temperatures, just inlet temperatures, outlet temperatures were given, and we have solved, we have calculated LMTD. But here, the variation of temperature of hot fluid is given with X. What does X stand for? X is measured from the inlet end, okay. And the variation of temperature for hot fluid is given, cold fluid is given. Look at carefully. Now, the cold fluid temperature is increasing and the hot fluid temperature is decreasing, and X is measured from here, X is measured from here. No problem at all. Observe here. Let me, how the temperature is varying with X. If you see, it is linear. It is linear. See the power of temperature, see the power of X, it is linear. See the power of temperature, see the power of this. Okay. Along when X is 0, what is the hot fluid temperature entry? When X is 0. So I will write this as when X is 0, hot fluid inlet, hot fluid inlet, hot fluid inlet. When X is 0, at the inlet X is 0. When X is 0, 80 minus 3 into 0, this is 0. 80 minus 0 is 80. No problem at all. So at the inlet, what is the cold fluid temperature? So at the inlet, X is 0. At the inlet, X is 0. When X is 0, 2 into 0 is 0. So therefore, T cold at the inlet is 20. No problem at all. And what is the length of the tube? The length of the tube is 10 meter. So let us calculate at the exit. At the exit, the hot fluid temperature TH2, at the exit it is 10, X is 10 at the exit, X is 10, X is 0, X is 10. So when it is 10, 10 into 3 is 30, 80 minus 30 is 50. Similarly, the cold fluid exit temperature, let us check. And X is 10 at the exit, X is 10. 10 into 2 is 20, 20 plus 20 is 40. That's it, sirs. That's it. That's it. Now it is a routine problem. So if you see the hot fluid, now I'll calculate delta T1. What is delta T1? It is TH1 minus TC1. So therefore, why like this, sir? Ek baar dekhna. If you understand carefully the variation, so this is X, this is X. What is happening to the hot fluid temperature? It is decreasing. When X is increasing, hot fluid temperature is decreasing. It is linear. Why linear? See the power of T and X. It is linear. Similarly, when X is increasing, the cold fluid temperature is increasing. Dekho, when X is increasing, it is plus. So therefore, it is increasing. When it is plus, it is increasing. It has a positive slope. On this axis, we have temperature. On this axis, we have length, that is X, X, X. So this is X is equal to 10. This is X is equal to 10. And this is X is equal to 0. And this is TH1. And this is TC1. And this is TH2. And this is TC2. And please observe clearly. So already we know the TH2 is 40 and TC2 is, sorry, TH2 is 50 and TC2 is 40. So what is delta T2? Delta T2 is TH2 minus TC2, 50 minus 40, that is 10. Similarly, TH1 is 80, this is 80, and TC1 is 20. So therefore, delta T1 is equal to TH1 minus TC1, 80 minus 20, that is 60. Now you may be wondering, sir, how do you know it is a parallel flow heat exchanger? It can be counter also now. Look at, X is measured from the inlet end. So if it is a counter flow heat exchanger, it will be like this. So when X is increasing, if it is a counter flow heat exchanger, when X is increasing, observe, when X is increasing, this temperature is, see, I'm moving. So I know that cold fluid temperature is increasing in this direction when X is decreasing. But when X is increasing, so there is a drop, there is a drop. So again, hot fluid temperature is also decreasing. In the positive X direction, both temperatures are decreasing. Please do not focus on the direction. I know the cold fluid is entering like this. But when X is decreasing, so when X is decreasing, cold fluid temperature is increasing. But when X is increasing, the cold fluid temperature is decreasing in this direction. In this direction, at this X, the cold fluid temperature is more, cold fluid temperature is less. So when X is increasing, it is decreasing. When X is increasing, hot fluid is decreasing. But in this case, it's not both decreasing. When X is increasing, one is decreasing. Yes, hot fluid is decreasing and the cold fluid is increasing. That's why it is a parallel flow heat exchanger. Hope the concept is clear. So because in the counter flow heat exchanger, when X is increasing, both will decrease, both will decrease. Understand carefully. So because in counter flow, one is like this, one is like this. So if I am measuring from one particular origin, so both in this direction, hot fluid temperature is decreasing, cold fluid is also decreasing. But cold fluid is increasing in this direction, so be careful. So it is a parallel fluid exchanger. Now, LMTD is very easy. If you want logarithmic mean temperature difference, it is delta T1 minus delta T2 by ln delta T1 by delta T2. So therefore, delta T1 is 60, delta T2 is, what is delta T2? It is 10 by ln of delta T1 by delta T2. So if you are calculating, I think I am getting the answer as, एक बार check करेंगे, 50 divided by log 6. 27.9 is the answer. So the answer is 27.9. So the answer is 27.9 degrees centigrade. So why I have given this question is, it is a very simple question. But why I gave this is, by looking at this temperature variation, you may get confused. That's it, sir. So in examination, you don't have to worry. Read the question properly, take the data properly, then everything will be crystal clear. No need for you to worry. Chalo. Let's start from the beginning now. So that's why I took the first question. First se le lenge hum. Let's take this question. Okay, please read the question. It's in front of you. One dimensional, I request everyone to catch this steady state. Whenever it is steady state, at every section, the heat transfer will be same. Whether you take this section or this section or this section or this section, for steady state, heat transfer is same. Okay. Now, what is he saying? The temperature distribution in two refractory blocks with thermal conductivities. So this has this is one block, this is another block. And there is a thermal contact resistance. You can clearly see, my dear students. Let me show you. A second, please. I'll take this color. So will it be okay? No, this is not good. So I will take this color. Chalo white hi le lenge. No tension at all. Ha. This is the temperature profile. So clearly, if you see, whenever there is a thermal contact resistance, the temperature profile is not continuous. What do you mean by continuous? So on the left side, on the right side of the interface, temperatures are not same. That is the meaning of continuous and discontinuous. So because of thermal contact resistance, the temperature is discontinuous. Temperature profile is discontinuous. So on the left side, it is 800. On the right side, it is 600. And on this side, it is 1000. On this side, it is T1. Now, what is he asking in the question? So find the temperature T1, okay, at the extreme right side of this block T1, and the thermal contact resistance is also asked in this question. Very simple, sir. You know that if you see electrical analogy, voltage drop is equal to current into electrical resistance. This we have studied Ohm's law, V is equal to IR. And the analogy in heat transfer is, so due to voltage drop, here it is temperature drop. Flow of current, flow of heat. Electrical resistance, thermal resistance. So this is one of the important equations in heat transfer. So delta T is equal to Q into R. Wonderful. So whenever you come across such questions, the first and foremost thing is calculate the heat transfer. Once the heat transfer is calculated, so why we are calculating heat transfer? Because that will help us calculate different parameters. How? Because once I calculate heat transfer, at every section the heat transfer will be same because it is a steady state. Chalo. So you can apply to any section. For example, I'll apply between these two sections. Now you may be wondering, sir, why are you applying between these two sections? Because this temperature is known to me as 1000. This temperature is known to me. I'm talking about this side of this. Okay. So it is 800. And I know the thickness of this. This is 1 meter. I know the thermal conductivity of this. Now you may be asking, sir, what is the area? Whenever the area is not given, and if it is not possible to calculate, we always calculate per unit area. That is for 1 meter square area. And you know, for a plain slab, the thermal resistance is given by L by Ka. For a plain slab, the thermal resistance is given by L by Ka. So delta T. Please listen carefully. First, I'll apply between these two delta T. This is 1000 and this is 800. So I'm applying between these two. 1000 minus 800. 1000 minus 800 is 200 is equal to Q into thermal resistance L by Ka. What is L? What is L? This is the thickness. L is 1. And what is the thermal conductivity? It is 2. And if area is not given, I'll take it as 1. So therefore, thermal resistance is given by L by Ka. The thickness is 1 meter. K is 2. So therefore, L by K is 2. K is 2. And area is 1. So if you are calculating, you will get Q as this 2 will come to the side. 200 into 2 is 400 watt. Of course, it is per meter square because we have calculated for 1 meter square area. Now the heat transfer is known. Now the question is, can I calculate this temperature by using that heat transfer? Why not, sirs? Why not? So look at, sirs. Here the temperature is 600. Here it is T1. So I will write delta T is equal to Q into R. Delta T. 60 minus T1. 600 minus T1 is equal to Q into R. Already we have calculated Q. It is a steady state, so everywhere the heat transfer is same. And what is Q? It is 400 into R. What is R? L by Ka. L by Ka. What is the length or thickness? Thickness is 1 by K. So this has a thermal conductivity of 1 and the area is 1. So this is 600 minus T1 is equal to 400. So T1 is equal to 200. Is it 200? Yes, my dear students, it is 200. So therefore, 400 is not correct, 500 is not correct, it is 200. Very good. Now, what is he asking? The thermal contact resistance. Very simple, sirs. You know the left side temperature as 800. You know the right side temperature as 600. In between these two, why there is a temperature drop? Maybe some gases or air is trapped. The thermal conductivity of air is very low. Therefore, the resistance is very large. As the resistance is very large, therefore, in a very small gap, there is a huge drop. So let me apply this equation. Delta T is Q into R. So in this, I will calculate the resistance. Delta T. It is 800. It is 600. So 800 minus 600 is equal to delta T. I am applying between these two. Delta T for this contact. 800, 600. Delta T. 800 minus 600 is 200. Is Q. Already Q is 400 into R. Delta T is Q into R. Now this is 200 and this is 400 into R. And you will get R as 200 by 400. It is 1 by 2, which is 0.5. So the thermal contact resistance is 0.5. So it is 200.5, 200.25. 0.25 is wrong. It is 0.5 is correct. This is the first answer. My dear students, is it clear? There is a possibility of this question. Slowly, we'll start some tough questions. Chalo. Let's go to the next question. Take this question. Read the question. Which among it is a multiple select question. Which among the following is or correct? देखो, Reynolds number देखो, rho is density, v is velocity, L is characteristic dimension by viscosity. Yes, it is correct. Rho v L by mu. This is correct. Nusselt number. You know that Nusselt number is HL by K. This is Nusselt number. And you know Boyer number, it is HL by K. But you have to be very, very careful. In Nusselt number, it is the thermal conductivity of fluid. And in Boyer number, it is the thermal conductivity of solid. That you have to see. In my regular classes, plus classes, I'll explain this very clearly, and I take about 40 minutes to give the difference, to mention the difference between Nusselt and Boyer number. In Nusselt number, and I gave you the physical significance also. Okay, right. So, H, characteristic dimension by K. Oh my God. Nusselt number, is it solid? Is thermal conductivity solid? Is it in Nusselt number, is it solid? No, it is absolutely wrong. So, therefore, this is wrong. Next, Schmidt number, kinematic viscosity of fluid by diffusivity. Please listen carefully. There is a difference between Prandtl number and Schmidt number. Prandtl number is mu by alpha. That is thermal diffusivity. Here, it's not thermal diffusivity. It is mass diffusivity. So, therefore, yes, it is mass diffusivity. If nothing is given, there is no problem at all. So, this is also correct. Because Schmidt number is used in mass transfer calculations. It is mass diffusivity or due to concentration difference. So, this is mass diffusivity. Kinematic viscosity of fluid by mass diffusivity. It is absolutely correct. Now, let's see what is Boyer number. So, please look at that. In case of Prandtl number, it is momentum diffusivity by thermal diffusivity. But here it is mass diffusivity that you should take care. In Schmidt number, it is mass diffusivity. So be careful. Yes, it is correct. Next, HL by K. And in Boyer number, here it has to be solid. So it has to be solid, but that fellow has given it as fluid. So this is absolutely wrong. This is wrong. So A and C are correct options. So who knows, tomorrow in examination, you may get question on Boyer number and Nusselt number. For a Boyer number, it should be solid. And for Nusselt number, it should be fluid. I had explained very clearly by giving physical meaning of these two terms in my regular classes. Okay, chalo. Now, let's proceed to the next question. Read this question. Aram se, no tension, sir. Let's do it very neatly. Air at 300 Kelvin is passed at a mass flow rate of, what is the mass? Okay, I'll take on the inlet temperature of air is how much, sir? 300. Okay. And the mass flow rate of air is how much? 1.5 kg per second. 1.5 kg per second. Okay. Now, through a metallic tube of inner diameter, and the diameter of the tube is given as how much, sir? Where is that? 0.08 meter. 0.08 meter. Okay. Now, the inner wall temperature of the tube is maintained at 700 Kelvin. It means, please listen carefully, air is passed through a metallic tube. Let me draw the figure. This is the tube. Let this be the wall of the tube. Okay. This is, and air is flowing through this. And the inner diameter is given as 0.08 meter. Now, and the flow rate is given. Okay, the temperature of air leaving the tube is 600. Okay, the inlet temperature of air is 300, and the exit temperature of air is 600 Kelvin. And one more thing, the inner wall surface or inner wall temperature of the pipe is maintained at, the surface temperature of the pipe is maintained at 700 Kelvin. So this is a question on constant surface temperature. I have discussed in my regular convection classes on Unacademy Plus, that is constant heat flux, constant surface temperature. In this case, the surface temperature is maintained constant. So therefore, the surface temperature is given as 700 Kelvin. Any other data given? Assuming that the heat occurs entirely by steady state convection, the length of the tube is, he is asking what is the length of the tube, and some other data is also given. What is the data? Let's see. The convective heat transfer coefficient is 500. Okay, the heat transfer coefficient is 500 watt per meter squared Kelvin. Next, any other data? The specific heat of air is given as 1080. The specific heat of air is given as 1080 joule per kg per Kelvin. And any other data given? Pi value, he is asking us to take it as 3.14. Let's do this question. And in my regular classes, I have derived the equation. That is, for a constant surface temperature, I do not know whether you remember or not. The equation that I derived is, so this year I am expecting a question on constant surface temperature. So don't blame me, sir, you are expecting, but it has not come in examination. It is only an expectation. It is an expectation. So Ts minus Te by Ts minus Ti is equal to minus Ha by m dot Cp. This I have given. This equation was derived by me in our regular classes. Now these are simply, revision classes or question series classes. Therefore, my dear students, I am not deriving the equation. So already I have derived this equation in my regular class. Okay, chalo. Now let's try to solve this. Now, through what area the convection is taking place? Pi d into L. Convection is taking place. The fluid is flowing like this. So pi d. So the fluid is flowing. So convection is taking place, pi d into L. So therefore, now I write Ln. The surface temperature is 700 and the exit temperature is 600. The surface temperature is 700 and the inlet temperature is 300 is equal to minus. What is H? I think H is given as 500 and into area by mass flow rate. What is the mass flow rate? I think it is given 1.5. It is given. Mass flow rate is given into the specific heat is 1080. And here students must be careful. What is the reason for that? The heat transfer coefficient is given in watt per meter squared per Kelvin. What does watt mean? It is joule per second. So whenever this is in watt, and try to keep specific heat also in joule, because it is not in kilowatt. It's not in kilowatt. If this is in kilowatt, keep this in kilojoule. It is already in watt, so therefore keep this in joule. So from this, I can easily calculate the area. Let me check, sir, what is the area? 1 second, please. Let's not waste time and we'll calculate. The area is coming out to be minus 500 1.5 0807. It is 4.49. So therefore, pi into dl is equal to 4.49 meter square. So pi, what is the inner diameter? 0.08 into L is equal to 4.49. Let me calculate. Ek bar, let me calculate, sirs. Pi into D into 4.49. I'm getting the answer as 17.86 meter. So it is a fill in the blank question if I am not wrong. It is a fill in the blank. Yes. So this is 17.8. So the length is asked, that is 17.8. Let me check, sir. 17.8. Yes. Take this question. Next. This is a very good question. Please read the question. Please read the question. This is a good question, sir. Slowly, now tough questions are coming. Slowly, tough questions are coming. Two large parallel planar walls are maintained at 1000 Kelvin and 500 Kelvin. Plane walls are maintained at 1000 Kelvin. Let me take this as T1. Let me take this as T2. And this is 500 Kelvin. And high to low, there is a heat transfer. Okay, right. Radiation parallel radiation shields are installed between two walls. Assume that the emissivity of walls and shields are equal. Okay. If the melting temperature of the shield is 900 Kelvin. Oh, this is very important. In this problem, this is very important. What is he saying? The melting temperature of radiation shield is 900. So when you are installing radiation shield, it should not melt. What does it mean? The temperature of the shield must be less than 900 Kelvin. That is the meaning here. So the maximum temperature of the shield can be around 899 or so, because if it is 900, it will melt. Okay. The maximum number of shields that can be installed between walls is. This is a good question, sir. Cool raho. मैं बताता हूं, sir. Okay. Now we are introducing a radiation shield. Okay. Wait. You know, my dear students, आराम से, heat transfer with shield by heat transfer without shield is 1 by n plus 1. This also I have derived in our regular class, but the condition for this equation is the emissivities of all shields are same, and the the plates are also of same emissivities. Okay, no problem at all. Okay, good. So heat transfer with shield, without shield is this. Okay, no problem at all. Now, if you observe here very clearly, आराम से sir, tension मत लेना. Let this temperature be, already it is given as 1000, and this temperature is given as 500 Kelvin. No problem at all. You know, my dear students, the heat transfer is given by sigma A T1 power 4 minus T2 power 4 by 1 by epsilon plus 1 between two parallel plates, between two larger plates. This equation was also derived by me in our regular classes. Okay, no problem at all. But in this problem, emissivities of both are same. So this can be written as 1 by epsilon plus 1 by epsilon. Why epsilon 1, epsilon 2 both are same? It is given in the problem. All emissivities are same. So 1 by epsilon plus 1 by epsilon is 2 by epsilon. So heat transfer without shield. We are calculating without shield. First we'll calculate without shield. First we'll calculate without shield. Without shield. What is the heat transfer? Sigma. Okay, area T1. Without shield. Let's calculate first without shield. T1, that is 1000 power 4 minus T2. What is T2? 500 power 4 by, देखो, sigma A. T1 is 1000, T2 is 500. Okay. 1 by epsilon, 1 by epsilon. Can I write this as 1 by epsilon plus 1 by epsilon as 2 by epsilon? Yes. 2 by epsilon minus 1. This is the equation of heat transfer without shield. Okay, no problem at all. Now observe here. Aram se observe here. Now, so if you understand carefully, my dear students, if I introduce a shield, look at carefully. If I introduce a shield, I don't know how many shields I'm introducing. I'm introducing shields. If I introduce shield, let this temperature, ये तो T1 है, ये तो T2 है, this is not changing, and let this temperature be some T3. Now observe here. Let this temperature be T3. No problem at all. You understand carefully. Emissivities are same. So what will be the heat transfer with shield? Let me write. With shield. I don't know how many are there. There are maybe n number of shields. No problem at all. उससे tension मत लेना. My question to you people is, can I take this value to be constant? Sigma is not changing, area is not changing, epsilon is not changing, it will be same. So therefore, heat transfer without shield, let me take this value as some K, some constant K into 1000 power 4 minus 500 power 4. No problem at all. Let us take one shield. What will be the heat transfer? If I take one shield, what will be the heat transfer? 1 by 1 plus 1. First, I'll do by trial and error. Then I will give you logically. First, I'll do by trial and error. Then I'll do logically. If number of shields, let me take it as 1. 1 plus 1, 2. So therefore, heat transfer with shield will be equal to, if n is equal to 1, if I take number of shields as 1, so if I take number of shields as 1, which shield will be equal to, listen carefully, which shield will be equal to, without shield by n is 1, 1 plus 1 is 2, means without shield by 2. So it will be without shield by 2. No problem at all. Wonderful, sir. Aram se. Now, can you tell me what is the heat transfer with shield? Very simple, sir. There is a shield. It is a steady state. Whatever the heat is entering here, same is leaving here. So either to calculate heat transfer, either I apply between these two or apply between these two. So it is similar to parallel plates. It is similar to parallel plates. Now what will be your equation? It will be, if I take with shield, it will be sigma A. I'm calculating with shield. Now this is with shield, this is T1, this is T3. So let me calculate between these two. Whatever heat is entering, it is going because it is a steady state. It is sigma A T1 power 4 minus T3 power 4 by 2 by epsilon minus 1. Same equation. Instead of T2, now it will be T1. Instead of without shield, it will be with shield. So whatever heat is coming, same is going. So therefore, up dekha. And you know very well, sigma A 2 by epsilon minus 1, its value is fixed. So let me write this as heat transfer with shield is equal to sigma A 2 by epsilon minus 1. What is sigma A 2 by epsilon minus 1? Idhar dekho, sigma A, it is taken as K. So it is K. This is K. T1 is 1000 power 4 minus T3 power 4. Very good. This is heat transfer with shield. But what is heat transfer with shield? Without by 2. So this can be written as heat transfer. If it is 1, without by 2. Heat transfer with shield is without by 2. This is without by 2. Heat transfer with shield is without by 2, and with shield is without by 2 is equal to K into 1000 power 4 minus T3 power 4. No problem at all. Now, already you know, take this 2 to this side. So heat transfer without shield is equal to, I will take 2 to this side. It will be 2K into 1000 power 4 minus T3 power 4. Cool. So what is the heat transfer without shield? It is K into 1000 power 4 minus 500 power 4 is equal to 2K into 1000 power 4 minus T3 power 4. So this K gets cancelled. So we are left with 1000 power 4 minus 500 power 4 is equal to 2 into 1000 power 4 minus T3 power 4. Let me calculate the value of T3. एक second रुको. 1000 power 4 minus 500 power 4, okay, by 2 is equal to I'm getting this temperature as 853.7. Is it reaching melting point? If I introduce one shield, is it reaching melting point? No. So it is safe. So I can use one shield. No problem at all. Next, let's see second shield. अब यहाँ पे एक बहुत important चीज देखना है सर. So let me erase this. So I'm getting 853 something. Means it is not reaching the melting point. So therefore I can use one. So now you may be saying, sir, can I use second also? Let me check, sir. एक second. Let me check. आराम से. कोई टेंशन नहीं सर. आराम से. Let me check. Now, if you observe clearly, this is one shield. Let us take this temperature is 1000 and this temperature is 500. Given. Now let me use many number of shields. Let me use, okay, 2 जो भी है. And it's very clear when number of shields are closer. So what will be the temperature of this shield when it is closer? So if I'm using one, I'll place somewhere in the middle. But if I use 2 or 3, it will be very close to this. When it is very close to this, it may reach this temperature easily. So therefore, it may be reaching 1000 or it may be reaching. So please understand carefully. If I am using more number of shields, observe clearly. Let me explain the concept. This is 1000 and this is 500. So if I am using one shield, listen sirs, if I am using one shield, already you have seen it is 853 point something. No problem at all. Look at carefully. I'm using 2 to 3. So अब देखो, what is the heat transfer? Heat transfer is, देखो, heat transfer, listen carefully. Heat transfer with shield by with shield by without shield is 1 by n plus 1. Now let me use two values, 2 shields. If I use 2 shields, now heat transfer with shield by heat transfer without shield is 1 by, let me take n as 2. अगर मैं 2 use कर रहा हूं, 2 plus 1 is 3. So therefore heat transfer with shield is heat transfer without shield by 3. Already we have calculated without shield. If there is no shield, my dear students, listen. If there is no shield, what will be the heat transfer? If there is no shield, heat transfer without, if there is no shield, it will be sigma A T1 power 4, no shield. If there is no shield, it is 1000, it is 500. 500 power 4 by 2 by epsilon minus 1. It is without shield. And we have taken this value as K. Therefore, heat transfer without shield is equal to, this is, already we know that, K into 1000 power 4 minus 500 power 4. This is without shield. Now, if you want with shield, what will be the equation, sirs? Look at carefully. Now, look at carefully. What will be the heat? Now, I am using two shields, let us say. What will be the equation? Let this be T1. Let this be T4. Let us take this to be T4. I don't know what is this T4. So, I will apply. I have used two shields. Let this be T4. So, this is the heat transfer with shield. What will be the equation? All emissivities are same. So, heat transfer with shield will be equal to, sigma A T1 power 4 is 1000 minus this temperature is T4 power 4, sorry, T4 liye, koi baat nahi, T4 by 2 by epsilon minus 1. But this value is K. This value is K. So heat transfer with shield is equal to K into 1000 power 4 minus T4 power 4. No problem at all. Now, what is heat transfer with shield? If I take this to this side, with shield will be equal to, without by 3. This is without by 3 is equal to K into 1000 power 4 minus T4 power 4. And what is without? This value I am substituting. Without is, you take 3 to this side. Without is this value. K into 1000 power 4 minus 500 power 4 is equal to 3K into 1000 power 4 minus T4 power 4. This K is gone. And if you are solving, let me check, sirs. एक बार मैं check करूंगा. 1000 power 4 minus 500 power 4 by 3, okay, plus 1000 plus 1000. And I'm getting this T4 as 910. Oh my God. Oh my God. Please understand, if I am using two shields, I am getting 910, which is crossing the melting point of 900. So if I use more than one, what is happening? It is crossing the temperature of melting point. So therefore I cannot use. So the maximum that I can use is 1. If I'm using 2, now it is crossing. So for 1, the temperature was 853. It is a very, very good question, sirs. It's a very good question. The theory related to this question, it was already given by me in my regular classes. So please understand, this is a beautiful question. This is a beautiful question. Next. Now, ये question देखो. This is also a good question. This is also a good question. Please read the question. So I'm trying my level best to give some wonderful questions. A cylindrical fin of diameter 24 is attached horizontally to a vertical wall. There is a wall. This is a wall. To this wall, a cylindrical fin is attached. Okay. And the diameter of this fin is given as 24. This is a very good question, sirs. I'll tell you what is the problem. This is a very good question. Finally, you may give the answer. But there is a small trick in this problem. There is a small trick in this problem. Dekho. Now, this is a beautiful question, sirs. I really love doing this question. I'll tell you where we are committing. First, I'll do. And you have to tell where the mistake is committed. First, I'll do it. Okay. I'll not say anything. Just understand. Okay. And the length is not given, I think. What is the length given? It is not given. In fact, that is to be calculated. Okay. A cylindrical fin of diameter is attached horizontally. Okay. The heat transfer from the fin is, listen carefully, 60% of the heat transfer if the entire fin were at the wall temperature. It is 60%. Look at carefully. 60% of the heat transfer if the entire fin were at the wall temperature? You know very well. If, see, let the wall temperature be T naught, let the ambient temperature be T ambient. We know, my dear students, now there is a heat transfer. Through the cross section, through this cross section, heat is conducted, and that conducted heat is conducting along the length, and subsequently it is convected from the surface area. Okay, no problem at all. Dear students, as the heat is conducted through the cross section and there is a temperature drop along the length. So that's why, as there is a, for example, suppose this temperature is 80 and the ambient is 20. So what is happening to it? So at this, what is the temperature difference between the fin surface and surroundings? 80 minus 20, 60. And when I move along the length, the temperature is decreasing because heat transfer occurs in the direction of decreasing temperature. So let us suppose here the temperature is 40. So here the surface temperature is 40, surrounding is 20. What is the difference? 40 minus 20 is 20 only. So here the difference is more, here the difference is less. That means when you are moving in this direction, now the heat transfer is decreasing. So he says, so when do you expect the heat transfer to be maximum? When the entire fin is assumed to be at the base temperature. Now that will give me the maximum temperature. And he said, so I will write this as Q maximum. Why Q maximum, sir? Look at 60% of the heat transfer if the entire fin were at the wall temperature. When the entire fin is at the wall temperature, if there is no drop, so for example, this is 100, 100, 100, 100, 100, 100. Everywhere the temperature is 100. So difference is 100 minus 20, 100 minus 20, 100 minus 20. So maximum difference. So if there is a drop in temperature, the difference is decreasing. That's why heat transfer is decreasing. So maximum heat transfer will occur when the temperature, when the entire fin is at the same temperature, at the base temperature. That's why generally we use fins with higher thermal conductivity, because if the thermal conductivity of the fin is large, the thermal resistance will be less, and thereby the drop in temperature along the length will be less. When the drop is less, along the length, when the drop is less, the available difference will be large, thereby the heat transfer will be maximum. You tell me, what will be the heat transfer? Listen carefully. What will be the heat transfer? So you know, if the entire fin is assumed, ab dekho, something like this, either dekho, this is the fin. If the entire, if this is T naught, base temperature, this is base temperature, base T naught. If the entire is at T naught minus P ambient, that is the difference. So what, through what area it is transferred? Surface area. Pi d into L. Pi d into L. Here I am missing something. Highlight this. I use the word I am missing something. I'll take it later. Look at carefully. Look at carefully. Now understand carefully. So heat transfer from fin is 0.6 times. So what will be the maximum heat transfer, sir? What will be the maximum heat transfer? When the entire fin is at the, I repeat, when the entire fin is at the base temperature. So everywhere the fin temperature is T naught, everywhere it is T naught, and the ambient is this. So what is the heat transfer? By convection, H A delta T, H area. What is that area? Pi d, yahan se convect ho raha hai, dekho. So from the surface, look at, from the base it is entering, and from the surface it is convected. So entire fin is assumed to be at the base temperature. So that is the maximum heat transfer. So what is the temperature? T naught, T naught, T naught, T naught, T naught. What is the surrounding? T ambient. So everywhere throughout the circumference, pi d into L for this complete area which is at T naught and ambient is T ambient. So therefore, what is the convective heat transfer? H A delta T. So therefore, H area is pi dl into delta T. So let me write that delta T as T naught. Here T naught represents base temperature minus ambient temperature. This is the maximum. So can I write heat transfer from fin is, he has given heat transfer from the fin is 60% of the heat transfer if the entire fin were at the wall temperature. Entire fin is at the wall temperature. So therefore it is 0.6 times this is heat transfer from fin is 0.6 Q maximum. What is Q maximum? H pi dl into theta naught. Very good, sirs. No problem at all. Thus, every question is important, please. Now, next. Other data is given. If the fin effectiveness is 10, what is the length? The effectiveness of the fin is given as 10. What is the effectiveness definition? It is heat transfer with fin, heat transfer without fin. Let me tell you. If you see this, now you have attached fin here. So actually you have attached it here. You have attached it here. If there is no fin, matlab this is the diameter. So this is the diameter. Yahan attach here. So now if there is no fin, look at, if there is no fin, let's see what is the heat transfer. Heat transfer with fin, heat transfer without fin. That is the effectiveness, which is 10. So you tell me, and this is temperature T0. The base is at T0. Ye to base hai, and ambient is T ambient. Now you tell me what is the heat transfer from this. If I want to calculate heat transfer without fin, there is no fin. I have removed fin. So if there is no fin, from this, what is the heat transfer? What is the heat transfer? It is heat transfer without fin is HA. What is this area? This area is cross-sectional area. So I will write this as pi by 4 d square HA delta T. What is delta T? This, look at sirs, this minus this, T0 minus T ambient and T0 minus T ambient. And I have taken T0 minus T ambient as theta naught. So I have taken it as theta naught. So therefore, heat transfer without fin is H into pi by 4 d square HA. Theta naught minus T ambient is theta naught. I have taken this as theta naught. This is our theta naught. So yahan put karna. So 10 is equal to heat transfer with fin. Already you know heat transfer with fin as 0.6 H pi dl theta naught. 10 is equal to heat transfer with fin 0.6 H pi dl theta naught by without fin. What is without fin? H pi by 4 d square theta naught. Theta naught is gone. H is gone. Pi is gone. D is gone. So therefore 10 is equal to, this 4 will go to the top. 4 will go to, this 4 will go to the top. There is 0.6 L. There is 0.6 L. Any other data? 0.6 L. Okay. So L is equal to, it will be 10 by 4 into 0.6. So there is something is missing here. यहाँ पे एक D आया तो 1D is left here. So 10 into D. So it is 10 into D. So what is D given? So if 10 into D, D is 24. If D is in mm, L will also be in mm. If D is in mm, L is also in mm. तो कितना आ रहा है sir? 2.4. So I will get L as 100 mm. Listen carefully. So 24, 4 into 0.6 is 2.4. 24 by 2.4 is 10. So 10 into 10 is 100. This is the length of the fin. But this is the wrong answer. This is the wrong answer. Any guesses? Any guesses? My dear students, I said we are missing something. We are committing one mistake. So what I did, you know, actually, you have taken only convection from this pi dl. You have not taken convection from this cross section. Tip se convection you have neglected. That means when you neglect convection from tip, that means actually this length will be the corrected length. Whatever length you are getting, it is the corrected length. Why, sirs? Because you have neglected. When you neglect the heat transfer at the tip, whatever the length you get is the corrected length. Whatever the length you get is the corrected length. This is the corrected length. This is not the actual length. Why, sirs? Because you have neglected the heat transfer from the tip. So I took the areas pi d into L. I took the area from this, it is entering pi d into L, but I have not taken this. So whatever the length, so that means I have taken such a length where the heat transfer from this is 0. Means whatever the length you are getting means actually there is a heat transfer from this. But if I want to neglect the heat transfer from this, so I will add some more length. So when I add some more length, that whatever the heat transfer was taking place from this area, that is occurring from this corrected length. So I repeat, sirs, ये बहुत ही अच्छा concept है sir. देखो, listen sirs, listen. So actually हमने calculate किया, we have calculated only from this, but there is a heat transfer from this. So what I have done is I have attached some more length. This is the actual length, my dear students. I have attached some more length. So whatever was taking place from this tip, now it is taking place from this. So whatever the length I have calculated, from here I have neglected. So whatever length you have calculated, it is actually the corrected length. So for a circular fin, the corrected length is actual length plus d by 4. He is not asking corrected length. You have calculated this 100 by neglecting the heat transfer at the tip. By neglecting the heat transfer at the tip means you have calculated this corrected length, so which is 100. So actual length is L and the diameter of the fin is 24 by 4. All are in mm. So this is 6. So the correct length is 100 minus 6, which is 94 mm. And I know that most of the students, they reach up to this and they give 100 as the answer. But the range is not 100, the range is 94 to 94, so you'll be out of the race. So be careful, my dear friend. Simple things are always complicated. I repeat, simple things are always complicated. So be careful, be careful, be careful. This is a beautiful question, sirs, because I have taken only pi dl. It means you are neglecting at the tip. So when you are neglecting at the tip, means actually there is a heat transfer at the tip. So I have added some more length so that whatever the tip heat transfer was taking place, now it is taking place from the surface area of that added length. So whatever you have calculated, it is the corrected length. But he is not asking corrected length, he is asking the actual length of the fin. This is a good question, sir. Now read the question. Heat transfer coefficient for a vapor condensing as a film on a vertical surface is given by, here students, this is the plate and there is a condensation. And there is one theory known as Nusselt theory. Nusselt theory for the film-wise condensation. According to this theory, there are some assumptions. So Nusselt theory is used. According to this theory, there are some assumptions. One second, please. One second, please. No, there are some assumptions. There are some assumptions. What are those assumptions? Let's see. Idhar dekho. Look at. The velocity of this film is assumed to be very, very small in this. So therefore, so when the velocity is very small, the axle change in velocity is negligible. So inertia forces are negligible. Therefore, predominantly viscous forces are there. And as the velocities are very, very small, heat transfer is occurring predominantly by conduction. There are some assumptions as per Nusselt theory. These are, if you want for condensing film coefficient to be calculated, I use Nusselt theory. This is very important. Okay, chalo. I have given all assumptions in my regular classes. Now take this question. For a shell and tube type heat exchanger, the clean overall heat transfer coefficient, is 250. And it is expected that the heat exchanger may be fouled during the operation, and the fouling resistance is given by, what is the fouling resistance? 0.001. Okay, the dirt overall heat transfer coefficient is, I have given this question also in my regular classes. 1 by, the clean heat transfer coefficient is given by 1 by dirty, sorry, please sirs. देखो 1 by, अगर आपको dirty चाहिए तो it will be clean plus fouling resistance. So 1 by the dirty heat transfer coefficient is given by 1 by clean. What is clean? It is 250. And what is the fouling resistance? It is given as 0.001. And therefore, if you calculate, I think you are getting this as 200. The dirty heat transfer coefficient, you are getting it as 200. It is 200. Okay, this is a simple question, but expected question. Take this. Very good question. Please read the question. Consider a solid slab of thickness 2L, and we may commit mistakes in this. The thickness is not L, but it is 2L. And uniform cross-sectional area. The volumetric heat generation is given by G, small g. Generally, we take heat generation as Q, but that fellow he is giving it as G. How does it matter? The slab loses heat by convection at both ends to air, and the heat transfer coefficient is H. Assume steady state one-dimensional heat transfer. The temperature profile within the slab is given by QL square by 2K, 1 minus, okay, let me write it on the next slide. The temperature profile is given by QL square by 2K. QL square by 2K. Okay, QL square by 2K into 1 minus X by L whole square plus TS. But यहाँ पे एक बहुत important point है. minus L to plus L. एक second रुको. Let me explain. This is the slab. This is the slab. Please, my dear students, this is the area. And this length is 2L. And let this area be A. This is also A. And look at carefully. Let this be the center. यहाँ से origin है X. This is positive and this is negative. And clearly here it is minus L, here it is minus L, and here it is plus L. And he said uniform heat generation. Okay, no problem at all. And this surface is maintained at Ts, and this surface is maintained at Ts. How do you know, sir? Very simple, sir. देखो, अगर x को minus L put कर रहा है, means here this surface. If you put x as minus L by plus L is minus 1. Minus 1 whole square is 1. 1 minus 1 is 0. So therefore it is, this is 0, T is Ts. If you put plus L, so L by L is 1. 1 square is 1. 1 minus 1 is 0. So therefore this is 0, again Ts. So it is symmetric on both sides. So therefore Ts. And obviously, where is the temperature maximum? Very simple. Obviously, where is the temperature maximum? It's very simple. Where is the temperature maximum? The temperature is maximum at the center. 1 second, please. Arun Mama? Class मध्ये Arun Mama, मी थोडे करतो, नंतर करतो, okay? मी एक half an hour 40 minutes मध्ये free होतो, okay? ठीक. Okay, now this is the area. Okay, observe clearly. ये हो गया sir, this is the one. No problem at all. Absolutely fine. Now, look at carefully. So what is happening? Let me tell you very clearly. What is happening is, this is the area. This is the, ये हो गया. Guess where the temperature is maximum? When it is a symmetric slab, or else you can differentiate this with respect to x. When you are differentiating, you get x is equal to 0. So dt by dx calculate karna, and you get the position. If I differentiate this, and there is no need to do, because it is a symmetric, whatever heat is generated, it is equally distributed. A half is going this side, half is going this side. So half is convected this side, half is convected this side. Whatever, it is a steady state. Whatever heat is generated in the slab, half is going this side, half is going this side. How do you know half is going this side? Because it is a symmetric uniform heat generation. Because this is at Ts, this is at Ts. Absolutely fine. So the temperature is maximum at the center. So he is asking, see the question. So the surface temperature is 350. This surface is 350. This surface is 350 and the ambient is 300. So this ambient is 300. And what is he asking in the problem? And oh, the bio number based on characteristic length is 0.5. कुछ नया ही दिख रहा ना सर? The bio number is given as 0.5. कुछ नया ही दिख रहा is 0.5. The maximum temperature in the slab is. Where do you find the maximum temperature? When it is a uniform heat generation, it's on both sides. So therefore, the maximum temperature is given by x is equal to 0 at the center. At the center, x is 0. X को 0 put करना. 0 तो ये 0 square ये तो 0 हो जाएगा. 1 minus 0 is 1. क्या होगा सर? Let me repeat. I want the maximum temperature. Where is the temperature maximum? At the center. So at the center means x0. X is measured from here. X is measured from here. Center say. So therefore x0 है. Temperature is maximum. So 0 by something. This is 0. 1 0 square 0 1. ये तो 1 आएगा. मतलब यही बचेगा. So therefore it is QL square by 2K plus TS. And he is asking what is the maximum temperature. And this is a very good question, sirs. Neither Q is given, L is given, K is given. कैसे करें सर इसको? कैसे करें? बहुत ही प्यारा सा प्रॉब्लम है. Bio number. What is bio number, sirs? It is HL by K, where L is characteristic dimension. How do I calculate the characteristic dimension in bio number? It is volume by surface area. He clearly said it is a one-dimensional. एक बार देखना question को. एक बार देखना. Please listen carefully. कहाँ पे है? Somewhere he has given one-dimensional. Somewhere it is given. Somewhere it is given. Yes, one-dimensional. So therefore, heat is transferred only in this direction, in this direction. No heat is transferred in this direction, one dimensional. Okay. देखो एक बार. What is the volume of this slab? Area. Let the area be A into length L. Don't write L because the length is 2L. Area into 2L. Area into 2L. Volume. Area into length. What is that length? 2L. By surface area. Look at, convection is occurring from this area. Convection is occurring from this area. So what is the total surface area? A plus A. Convection is occurring from this area. Convection is occurring from this area. So what is the total area? It is 2A. So therefore, 2 is gone A. So the characteristic dimension is L. So therefore, the Boyer number is given by HL by K. One more beautiful concept. What is that concept? It is a steady state. So whatever the heat is generated in the slab, it should be convected from this side, convected from this side, and it is a symmetric slab. So what is the total heat generation? It is heat generation per unit volume into total volume. So the total heat generated is heat generated per unit volume into volume. What is the volume? Area is A and the length is 2L. Area is A and the length is 2L. Area is A and the length is 2L. So this is the total heat generation. Total heat generation. And where is that heat going? Half is going to this side, half is going to this side. And if you observe clearly, and whatever it is a steady state, whatever is generated, it should go out. Whatever is generated, it should go out. So half heat, what is the heat transfer coefficient? H. So this will be equal to HA into delta T. HA into delta T. What is delta T? This is 350 and this is 300. TS minus 300, so that is 50. But unfortunately, I cannot equate this. Why? Because total heat generated is this one. So total heat generation into volume, that is the total heat generation. So as it is a total heat generation, half is going this side, half is going that side. So therefore, it is only this side. So remaining half is, therefore, I'll multiply with 2y. So HA delta T, HA delta T, HA delta T, HA delta T. No problem at all. No problem. That's why I have multiplied with 2, because HA delta T is this side, HA delta C that side. So therefore total ho gaya. Now let me cancel. Area. Anything more? 2 is gone. So Q into L by H is equal to 50. Q into L by H is 50. Somehow ये वैल्यू लाने की कोशिश करना. देखो सर, Boyer number is given in the problem as 0.5. Already you know 0.5. एक बार ये दोनों मल्टीप्लाई करो. Let's see. HL by K into QL by H. I repeat, sirs. HL by K is 0.5. 0.5. QL by H is 50. So HL by K is 0.5 and QL by H is 50. तो कितना आएगा सर? देखो, I think QHH is gone. So QL square by K. L into L is L square. QL square by K is 0.5 into this is 25. तो देखो एक बार. QL square by K का वैल्यू कितना है सर? 25. So there is 2 also. Half. So the maximum temperature is half. 2 है देखो. QL square by K. QL square by K. What is QL square by K? What is QL square by K? QL square by K is 25 plus TS. The surface temperature is given as 350. Surface temperature is 350. So therefore, 25 by 2 is 12.5. 350 plus 12.5 is 362.5 Kelvin. This is a wonderful question. Are they in Kelvin? All are in Kelvin. So this is a good question. So the maximum temperature is 362.5. Let me check. The maximum temperature is 362.5 Kelvin. That is the right answer. Again, a good question, sirs, for good students. Now take this question. Please take this question. This is a simple, straightforward question. Let's see how many questions are left. How many are left? ये क्या है? Okay, mass flow rate पूछा. ये तो already we have done. And ये भी. चलो कर लेंगे sir. आराम से कर लेंगे. No tension. No tension. Don't worry. Don't worry. हाँ. Take this question. Read the question. Please read the question. Read the question. A hollow cylinder of equal length and diameter are same. Equal length and inner diameter, L is deep, is seated at both the ends. Okay. Is sealed, not seated. is sealed at both the ends with flat plates. So there is a hollow cylinder and it is sealed with flat plates as shown in the figure. This is given as A1. This area is taken as A1. This hollow cylinder is taken as A2 and the bottom area is taken as A3. There are three surfaces. It's something like this. This is A2, this is A1 and this is A3. Flat, circular and cylindrical. Okay, something like this. This is A2. ऊपर वाला cover is A1. नीचे वाला cover is A3. Now, you know very well, summation rule F11 plus F12 plus F13 is equal to 1. Can you tell me what is F11? It is a flat surface. So whatever the radiation is emitted from 1, nothing is falling on itself. So therefore, this is a flat surface. So whatever is emitted from 1, everything is going to the other surface. So F11 is 0. So therefore, F11 is 0. So F12 plus F13 is equal to 1. I think something is given. F13 is given in the problem as 3 minus 2 root 2. F13 is given as क्या दिया है? F13 3 minus 2 root 2. Okay. So therefore, F12 will be equal to 1 minus F13. F12 is 1 minus F13. So F12 is equal to 1 minus F13 is 3 minus 2 root 2. So therefore, F12 will be equal to, ये कितना होगा? Minus of minus is plus 2 root 2 minus of. So 1 minus 3 is minus 2. So therefore, F12 is equal to 2 को common लेंगे, root 2 minus 1. So therefore, he is not asking F12, he is asking, look at F21, 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 F21. So therefore, a reciprocity theorem, A1 F12 is equal to A2 F21. So therefore, F21 is equal to A1 by A2 into F12. So therefore, F21 is equal to A1. What is A1, sirs? What is A1, sirs? What is A1? This is A1, circular area, pi by 4 d square. Circular area, let me explain very clearly. This is a circular area. यहाँ से पूरा radiation आ रहा है from the surface. So A1 is pi by 4 d square by A2. What is A2? So pi d into L. Because देखो एक बार, यहाँ से हो रहा है, everything from this pi d curved area, pi d into L. So therefore, A2 is pi d. Length is also d because here L is equal to d given into A1 by F12. What is F12? 2 into root 2 minus 1. F12 is already known. अब देखो, pi is gone, d square is gone. So therefore, F21 is equal to 2 into root 2 minus 1. 2 into root 2 minus 1 by 4. So therefore, ये गया. So F21 is equal to root 2 minus 1 by 2. Let me check. Root 2 minus 1 by 2. Yes, root 2 minus 1 by 2. So B is the right answer. So let's check this. अभी कितने हैं रे? Yes. Now we have 2 more questions. Let's do this. ये करेंगे सर. A perfectly insulated double pipe heat exchanger is operating at steady state. Saturated steam enters the inner pipe at 100 and leaves at 100. Oh my God, it is a phase change heat exchanger. So whenever it is a phase change heat exchanger, it doesn't matter whether it is a parallel flow or counter flow heat exchanger. So whenever it is a phase change heat exchanger, it doesn't matter whether it is a parallel. So hot fluid is entering at 100 and it is leaving at 100. There is no change in temperature. And look at, water enters at 75 and leaves at 95. So water is entering at a 75 and water is leaving at 95. Observe here. So why you have taken parallel flow? It doesn't matter whether it is a parallel or counter flow whenever it is a phase change heat exchanger. So it is a phase change heat exchanger because saturated steam is entering and saturated water is leaving. So it is a phase change heat exchanger. No problem at all. Now, my dear students, what is delta T1? This is 100. So it is TH1 minus TC1, 100 minus 75. 100 minus 75, it is 25. What is delta T2? 100 minus 95. 100 minus TH2 minus TC2, 100 minus 95 is 5. So what is LMTD? LMTD is delta T1 minus delta T2 by ln delta T1 by delta T2. So therefore, The logarithmic mean temperature difference is given by delta T1 is 25, delta T2 is 5 by ln 25 by 5. Can you give me the value of delta T1? एक बार check करता हूँ sir. 20 by, this is 20 divided by ln pi ना 12.42. So delta Tm is 12.43 ले लेंगे. Okay, no problem at all. No problem at all. Okay, is it degree centigrade? Because all temperatures are in centigrade. No problem. So now what is he asking? What is the mass flow rate of cooling water? So first let's calculate the heat transfer. The heat transfer is given by UA delta Tm. Okay, where is that? कहाँ गया रे? The overall heat transfer coefficient is given and the heat transfer area is also given. So overall heat transfer coefficient is 1 kilowatt per meter square and the area is also 1. So therefore, total heat transfer is given by overall heat transfer coefficient is given as 1 kilowatt. I am converting from kilowatt to watt and the area is given as 1 and delta Tm. What is delta Tm? 12.43. So this is, so if you observe clearly, you will get this value. This is in watt per meter square per Kelvin. So you will get this as 12.43 into 10 power 3 watt. But you know Q is equal to mc delta T and Q is 12.43 into 10 power 3 is equal to mass flow rate of water. And what is the specific, and here you are going to commit mistake. As this is in watt, keep the specific heat of water in joule, not kilojoule. So therefore, what is the specific heat given? Is it given, sirs? Nahi diya. 4.2, no problem. So 4200. Why? Because this I have kept in watt. So if this is in watt, watt means joule per second. This should be in joule. mc delta T of water. So water का temperature difference, water mass flow rate, water specific heat, water temperature difference. And what is the temperature difference of water? Water is entering at 75, leaving at 95. What is the temperature difference of water? 95 minus 75. 95 minus 75. So it is 95 minus 75. You'll get the mass flow rate of water in kg per second. Let me check, sirs. Let me check. 12.43. Okay. Divided by 4200 divided by 20. And I'm getting the mass flow rate as 0.148 kilogram per second. 0.148 kilogram per second. Let me check, sir, whether it is right or wrong. 0.148. शायद सही है. I don't have value. Yes, it is correct. It's correct. Already we have solved this question. Ye wala, last question. Please read the question. Please underline this term, infinitely long. Fin. And the ambient temperature is 27. Okay. The steady state one-dimensional energy balance on an element of fin is shown. ये तो हम already derive किए. Okay, this is given. And what is he asking in the problem? The base, this is the fin. Please look at carefully. This is the fin. The base temperature, let it be T0, and the ambient temperature be T ambient. The base temperature is given as how much, sir? What is the base temperature? Where is that? Somewhere it is given. So the base temperature is 227. The base temperature is 227. And what is the ambient temperature? The ambient temperature is 27. So the ambient temperature is 27 degrees centigrade. Okay. Now what is he saying? And I think M value is also given. So somewhere M is given. Somewhere M is given. कहाँ पे दिया है? Somewhere M is given. Yes. The value of M is 0.04. Unit per centimeter. Listen, sirs. Listen. It is per centimeter given. Okay, no problem. And you know, my dear students, I have derived in my regular class for infinitely long fin, theta by theta naught is equal to e power minus mx. I gave this equation. What is theta? It is T minus T ambient. What is theta naught? T naught minus T ambient. What is T? It is the temperature at any distance x. T is the temperature at any distance x. This was the equation derived by me when it is infinitely long fin. Theta. What is theta? T minus T ambient by theta naught, that is T naught minus T ambient, is equal to e power minus one more thing. If this is in centimeter, x should also be in centimeter because it should be dimensionless. So x at what value he is asking? He is asking at x is equal to 25 centimeter. Means at x is equal to 25 centimeter, इस लेंथ पे वो पूछ रहा है. What is he asking? Temperature. He is asking temperature. He is asking temperature at x is equal to 25 centimeter. So m is 0.04 and x is 25. This is per centimeter. This is centimeter, so unitless. So you will get T, I don't know, and the ambient temperature is 27. So if this is in degree centigrade, this will be in degree centigrade. T minus T ambient is 27 by T naught. What is T naught? 227 minus ambient is 27, and that is equal to e power, I think, how much is this? 4 by 100 is, I think it is minus 1. So let me calculate this value, says. This value is 0.3678 into 200. ये तो 200 हो जाएगा, and plus 27, this 27. So I am getting the temperature as 100.5 degrees centigrade. He is asking the temperature at 25 centimeter. So what is he asking? The value of m is given, the temperature at the base is given, then the temperature in degree centigrade at x is equal to 25 is 100.5 degrees centigrade. So this completes, yes, all questions are over. Yes. So thank you, my dear students. So I'll come up with some more very good questions. Thank you, and please leave comments if you are happy with this series. Thank you. God bless you.